So now, our next guest is Melanie Mitchell with the talk Abstraction and Analogy in AI, the role of core knowledge systems. So Melanie Mitchell received her PhD in computer science from Michigan University. As of now, she is the Davis Professor at the Santa Fe Institute, where she also originated the Complexity Explorer platform, offering educational resources related to the field of complex systems. Her current research interests are conceptual abstraction, analogy making, and visual recognition in artificial intelligence systems. Melanie is also an author of many books and scholarly articles, among others, Complexity, Guided Tour, which won the 2010 Phi Beta Kappa Science Book Award. And her latest book is Artificial Intelligence, a guide for thinking humans. Thank you for accepting our invitation, and the floor is yours.
Thank you. Can you hear me okay?
Yes, we can hear you.
Great. I will share my slides. Okay. Oops. All right. So thank you to the organizers for this really interesting symposium. I'm going to be talking about abstraction and analogy in AI. So many of you may be aware of the origins of AI, some of which are linked to this workshop that was proposed in 1955 by these pioneers of AI. And in their proposal, they listed some of the things they thought would be most important to solve. They thought that they would solve it, a large part of it, within a summer. It actually is taking a lot longer. But here are some of the things that they thought would be important: language, abstractions and concepts, and self-improvement. Well, this particular question of forming abstractions and concepts seems to be one of the most difficult for AI systems, whether they be symbolic or neural or statistical or whatever. And this is what I'm interested in. And I think that the notion of innateness actually plays an important role. So as Alison Gopnik mentioned earlier, that there is some psychological evidence, especially as described by Elizabeth Spelke and her colleagues, that infants are born with some kind of core knowledge, the innate systems of core knowledge that serve as the foundation for building the kinds of conceptual abstractions that we humans are so good at. And these involve objects and their interactions, agents and their actions, numbers and quantities, and the notion of space or the geometry of the environment. So these are what Spelke et al. Are proposing are the basically innate foundations of the rest of our knowledge that we develop over our lifetime. But moreover, they propose that we're also born with a domain-independent system that can combine the outputs of these systems in a compositional way. Okay, so the claim of my talk is that these kinds of abstract concepts that are built on top of core knowledge are created via analogy. Okay, so this has been a proposal of Douglas Hofstadter for decades, and he's written extensively on this topic, along most recently a book on analogy with his co-author Emmanuel Sander. So just as an example of an abstract concept that is built on core knowledge, think of the concept of increasing order. So arranging things in an increasing order, very, very basic idea. Okay, so, we have the notion of like increasing order of size of an object. A little bit more abstractly, perhaps the increasing order of brightness. These are tied to our sensory modalities. Similarly, the increasing order of, say, a musical sequence, or the volume of a particular musical note. often children are given challenge of putting in order temporal events. And, this is kind of almost an intelligence test to be able to figure out how to order these temporal events. But even more abstractly, we have notions of increasing order in many adult activities, such as like military ranks in the US, or say the impacts of war, biosafety levels of risk, levels of complexity in natural systems that can be abstracted in terms of things like increasing fractal dimension. And all of these are just to give you the idea that these basic core concepts are formed via analogy that we are almost completely unconscious of. We don't even see these as analogies, but these abstractions that we form throughout life are powered really by these kinds of analogies. And this is how Hofstadter defines concept itself, as a package of analogy. Okay, so how is it that we could enable AI systems to grasp abstract concepts via analogy with the kinds of core knowledge that we might be able to give it? So I've been working for many years on this kind of thing, and most people, many people at least in the AI world, focus on this question via idealized domains. One very popular one is to look at Raven's progressive matrices. So Raven's progressive matrices were first invented as a kind of IQ test for humans. So here's an example. Here's a matrix of 8 elements, and the elements progress in some way, through the rows and the columns. And here are the candidate answers over here on the right. And so what you're supposed to do is figure out which of these answers should go in the final 9th slot of the matrix. And you can probably see very easily here, we have this nice example of a decreasing sequence, perhaps, if you read from left to right, of different geometric shapes. And so the correct answer would be, this smaller triangle. So a lot of people in the AI world have adopted Raven's progressive matrices as a way to try and teach machines to build abstract concepts, or to evaluate their ability to deal with abstract concepts. These Raven's matrices can get much more complicated. This is perhaps a slightly more complicated version of the sequence problem, because we have these, these arrows added on. And here's an even more complicated version where, we have increased sequence in number of objects. Also, we have an increase in the number of sides of the object. And we have notions of first or rightmost, last or leftmost or rightmost, I would say. And these are the kinds of sort of combined combinatorial concepts that people have to deal with, or machines, when faced with these Raven's problems. So there's been a lot of work on getting, for instance, deep learning systems to learn to solve these Raven's problems, but it turns out that they have a lot of limitations, and they tend to be fairly brittle. An even more unmet challenge for AI are the Bongard problems, which some of you may have seen. These were proposed in the 1960s by a Russian computer scientist, Mikhail Bongard, who, as a challenge for AI systems, the idea here now is that we have 6 figures on the left and 6 figures on the right, and the machine is supposed to determine what is the sort of distinguishing concept here that's contrasted with the distinguishing concept on the other side. And the Bongard problems also challenge the problem solver to find abstractions, and they by analogy. So here, for instance, it seems that, you know, it's kind of like that increasing sequence problem there. Here we have a sort of containedness, levels of containedness, where here there's only one level of containedness, but here we have two levels of containedness. Here's another similar problem of sort of the sequence, where the idea of, I'll let you look at it for a minute, probably see it quickly, but the notion of 3 is contrasted with the notion of 4 on the other side, where this notion of 3, this core concept, can be abstracted in all these various ways. And finally, another 3 versus 4 Vanguard problem, abstracted in a different way. Okay, the domain that I myself have worked with are the letter string analogies that were formulated by Hofstadter initially, which were formulated as a way to approach abstraction and analogy that is, in some ways, at least superficially, more simple than the Ravens domain and the Vanguard domain, which continue to be extremely challenging. But here we sort of have an explicit analogy. ABC changes to ABD. What does this new letter string change to? So now we have to say, what is the abstract concept that we should apply to both letter strings to make the same change? Same being analogously the same, not identically the same, because identically the same would be just change anything to ABD. So we don't want to do that. So this is, you know, another example of a sequence. And here we have an example of a sequence, but it's slightly different because obviously we have these groupings of letters as opposed to single letters. So explicitly here, what's explicit here is that we have to take our concepts and let them be flexible. So if we want to say, for instance, that the rightmost letter is replaced by its successor, in the bottom string, the notion of letter is, the role of letter is played actually by a grouping of letters. So we can't be literal about the changes that we want to make. Another example would be this one, where instead of grouping, we actually reverse the order of the sequence. And so we might say, instead of replace the rightmost letter, we would say replace here the leftmost letter, because the ordering is different. In this problem, we have to find some kind of abstract similarity between this string ABC and this string MRRJJJ. And you might notice that instead of increasing alphabetically, we're increasing numerically with 1 letter, 2 letters, 3 letters. So we might replace this with, say, MRR and 4 Js, the successor in the numerical world. And finally, this one's another extension of the notion of a sequence. Here, if you look at it carefully, you might notice that there's a sequential structure if we group this as A, AB, ABC. And so the successor of the rightmost letter, or here would be the successor of this rightmost sequence, ABCD. So these are all examples of these idealized ways to deal with this notion of taking knowledge, core knowledge that you might have about a domain, and applying it adaptively. So Hofstadter proposed an architecture way back in 1984, proposed this architecture for this program that would solve these letter string analogies. And the main idea was that analogy making should consist of dynamically adapting prior knowledge or core knowledge or innate knowledge, if you like, to compositionally represent new situations, allowing what he called conceptual slippage, where the slippage is that flexible replacement of one concept by another, like successor by predecessor, or letter by grouping of letters, things like that. And the idea was not necessarily just to solve these letter string analogy problems, but to build a more general architecture for applying some kind of core knowledge system to any domain, and to be able to adaptively represent new situations that come about. So this was my assignment when I went to work for Hofstadter as a PhD student, was to build this system. And the architecture consisted of different components, a concept network, which here's a sort of view of the core knowledge of this system, if you will, which involved the letters of the alphabet, and some spatial and conceptual attributes and relationships, like sameness or oppositeness or successorness, predecessorness, left, right, sameness group, successor group, predecessor group for groupings of letters, first in the alphabet, last in the alphabet. And so you can think of this as kind of a microcosm of what might be the core knowledge of a young child trying to make sense of the situations it encounters by trying to adaptively apply its concepts. And the way that our program did this with a new situation, which is a new set of letter string analogy, a new letter string analogy, was to separate this network of prior concepts with a sort of working memory, an explicit workspace where these concepts could be adaptively applied. Okay, and they were applied by what we called perceptual agents or codelets, which were agents, literally agents of concepts in the concept network, trying to apply those concepts to a new situation. So they mediated the long-term knowledge, prior knowledge of the system with what was encountered in the world, namely a new analogy problem. And they did this in a very stochastic way that was controlled by what was encountered in the environment, but also by what was activated in the network. So the concepts could be activated to be, say, more or less relevant. For example, the program one of these agents might randomly encounter these two letters and describe it as a sameness group, same letter. Okay, which then would activate this concept and produce a top-down pressure to find other examples of that concept. So there was this interleaving of bottom-up perceptual and top-down conceptual processes of making sense of this, or successorship, sameness in mappings across strings, and this stochastic set of codelets was controlled by a temperature variable. So like Allison earlier described in her discussion of exploitation, it's kind of a simulated annealing process where temperature starts high and then everything's more random. Temperature then gets lowered and things become more deterministic. So they start out more exploring and then end up more exploiting. Well, this is what our temperature did, except for one important difference. The temperature itself was controlled by the structures, these perceptual structures that were built in the workspace. So rather than being a top-down control mechanism, it was a feedback mechanism where when the program had very little kind of organized sense of how to represent the input in the workspace, the temperature was high. which would then feed back to make things more random and more exploratory. But when more structure was built, the temperature would be lowered, which made the system more exploiting the structure that it already had. So let me show you a quick little video of the program running. So I'm showing you the workspace and the temperature here, but not the concept network, because it's a little bit too hard to display everything. But in the background, the concept network, the different concepts are getting activated and creating top-down processes. So what you're going to see is a bunch of, at the beginning, temperature is maximal. You're going to see a bunch of exploration by different perceptual agents that then try and build structures. And these little lightning bolts are explorations looking for potential relationships in a very kind of random way. But when some possible relationship is discovered, like, for instance, the leftmost letter corresponds to the leftmost letter, the two strings, a structure is built, can get destroyed by other structures, or it can get progressively stronger, which is indicated by the solidness of the line. And as you can see, the temperature getting lower, the system is kind of freezing in on a particular way of making sense of this situation, and is able to describe these two strings as actually predecessor relations, because it doesn't have any left to right reading bias. It will go either direction. And it's seen these as abstractly similar because one consists of letters that progress in a sequence, and the other consists of little letter groups that progress in a sequence. And then it can describe this as, well, we've reversed the direction of this, these letters. Now we're going to reverse the direction of the groups. So it's able to make a description of what's going on here and then translate that description for what's appropriate in the new situation. Okay. So, oops. All right, I have to get to the next slide here. So this system and many others, though my system was described in my book about analogy making, Hofstadter and other his graduate students and postdocs, which I was one, described all of their various approaches using the same architecture in different idealized domains in this book. And I just wanted to isolate some of what I think are the important ideas and what I think are some things we can take going forward in making progress on abstraction and analogy in AI. So one idea is that this architecture models analogy not as a sort of pure reasoning process on already represented situations, but more as a perceptual process in which representation is actively built up over time. It's a dynamic system which continually adapts its prior or core concepts to its bottom-up perceptions and the perceived context. And as I mentioned, it allows this emergent transition as it goes through its perceptual process from a very more bottom-up, parallel, more exploratory mode of processing to one that's more top-down, serial, and deterministic and exploitatory. So Copycat can dynamically adapt its prior concepts to new situations in its idealized domain. But one thing you might have noticed is it doesn't form new permanent concepts beyond what it's given in its core repertoire. And this is a big question. How do you form new permanent concepts? And I think that's really the next frontier for this kind of thing. Francois Chollet of Google wrote an interesting paper a couple years ago called On the Measure of Intelligence, where he proposed a particular kind of corpus called the ARC corpus, abstraction and reasoning corpus, for this kind of abstract reasoning, abstract concept formation. It's similar to Copycat, except it's a grid of colored squares instead of letter strings. And the idea is that you have a task, which is way of transforming a grid, one grid to another. And you give several examples of that. And now you say, do the same thing to a new grid. And you can do this. He has many very beautiful examples of this, which you can see, I think, on the GitHub site, of different kinds of transformations that he explicitly based on Spelke's core knowledge hypothesis. But anyway, it's a really beautiful set of idealized problems, and he proposed himself that the way to approach this is a probabilistic program synthesis approach, which I'm not quite so sure is the right approach, but we'll see. And the idea here is that you rely on very few shot learning, sort of like Copycat, which had one shot learning, which says, I give you ABC to ABD. Now apply that, do the same thing to the new string. Here we have 3 examples, and now it's saying do the same thing to this matrix, this grid. And interestingly, Cholet put this up as a Kaggle challenge with prize money, and got a bunch of people trying to solve these problems. And they got, I think the best programs got about 30% of the test cases right. They were given 3 guesses on each test case, but not in a very general way. So I think it's still wide open. And I think it's a really nice complement to all of these different other idealized domains. So the question is, how do we make progress on this area? Well, I think we really, in AI, we need to have a common suite of these challenging tasks that explore this idea of abstraction of core knowledge. And I'm a big advocate of these idealized domains. You know, some people will say these are not real world domains, they're toy domains, and we should really be working on real world analogy. But the problem is, in real world analogy, we have like human language, and it's harder to be explicit about what our prior core knowledge is and what assumptions are needed. Whereas in these idealized domains, we can be very explicit. And by avoiding these language-based tasks, we can really avoid anthropomorphizing what a system has achieved. So you really see that with, you know, language systems like GPT-3, which is, we humans sort of give it more credit than it probably deserves, because we are applying our sort of rich conceptual background to the language that it generates, that it doesn't really have. And I think the evaluation has to be really a performance across different tasks. So I showed you like this all these different domains that use this idea of increasing sequence. And I think that we really need to evaluate systems on their ability to make these abstract analogies across these different domains, not just within one domain. And I think to be able to generate their own solutions, as opposed to simply recognize them, like people do in deep learning community, ability to abstract with only a few examples, and also robustness to modifications and concepts, like different versions of this like increasing sequence and more complex versions, being able to scale. So I think these are the dimensions along which we should evaluate systems, as opposed to simple, you know, accuracy, which is what most people use. And I guess that's it. I'll stop there and answer questions. Let me stop sharing. Okay, good.
Thank you for the talk. And I think we have a question from Paul Tisek.
Yeah, so I thought that was really interesting. And I actually found it quite surprising, actually, though, that you were describing what looks to me kind of like you said at the end. It's a very specific kind of domain of analogy that seems to almost assume that intelligence is something that we can sort of distill and separate out of everything else that humans do. And let's just define it clearly and then address it sort of in a focused manner. But it seems to me that that's sort of, in a sense, poised to fall into that trap that a lot of AI fell into of being very good at an extremely narrow context and completely incapable of going beyond the context. And the reason it surprises me that you're giving this example, I mean, maybe this is more your past than your present is that I thought you, in other work, have sort of supported a kind of a Piaget-like idea of intelligence being constructed on much more sort of concrete activity of pushing things around and putting things inside other things, sort of much more sensory motor level interactions, which then abstraction builds on those. And it seems to me that by doing this kind of thing and saying, let's devise these extremely abstract problems to get at meaning, to me, it just kind of seems like that's exactly not in line with that proposal, that meaning really comes from fundamental concrete interactions, and then then you can have the abstraction. So maybe you can comment on that.
Okay, so Paul is using his prior knowledge of me.
Yeah, well, I haven't. Yeah, so I don't really know all your work. I've just seen a few of your talks. So.
No, I think that's a really great
could be way off.
Yeah, no, it's a really great question, and you know, I do feel this kind of I don't know how to kind of pull in both directions. So I do believe that our intelligence is, in a large sense, very embodied and requires, you know, very much based on physical experience. I also think that we can make progress in AI by looking at very idealized domains. So maybe those two things are completely opposed. I don't think they necessarily are. You know, I'm not saying that if we get a machine that solves all of these different kinds of problems, like Vanguard problems, Ravens, etc., that machine's now going to be able to go out in the world and make real world analogies. But I think that we will have gained some insight into how kind of prior knowledge could be abstracted. And that will help us in figuring out the much harder problem of how to have a more physically realistic embodied system.
You think the insights of looking at how these kinds of problems can be solved could be translated into understanding how a child learns increasingly sophisticated sort of abstracted knowledge, sort of from just, you know, putting blocks together and putting things inside other things. So you think the principles will be the same within the abstract domain as in a more sort of concrete domain?
I think it's possible. It's possible they won't, but I think it's possible they will. You know, putting things inside other things is like a great example of a core knowledge thing, where it's like something, the notion of containment is always a popular example. But I think you can give lots of interesting examples of containment even in these idealized domains. You can say, you know, here's an example of containment. Here's another example of containment that looks really different from the original example of containment. And yet it's abstractly the same concept. How do you recognize that? And I think even, you know, Alison's example with the Blixit, I can't remember exactly the name for it, but the little blocks that she had, you know, she has, I've seen her in other talks give examples where, you know, the children are trying to make sense of containment kinds of things and different relationships. And I do think those kinds of things can be captured in these domains. You know, I don't have a robot that's like picking up blocks and putting things inside other things. And I think it's a kind of an open question of how much do you need that or not to get insight into cognitive principles. So,
well, it just seems to me that meaning is always sort of outside in. It's sort of the broad context and then specific abstractions. But the meaning of those specific abstractions always sort of comes from a larger context. And if you start with the narrow, then how do you get to meaning outside of the context, right? In other words, the meaning of abstraction, things like words that you utter, comes from the things that those words produce in your world. You know, other people move around and stuff and bring you things.
Right.
So it's sort of the very specific thing that you do to just push the world in particular ways, and the meaning of the words is in that interaction. But if you start with the abstracted things, more syntactic, then how do you go outward into the meaning of the larger context? That seems to me the difficulty that AI has always struggled with, and is still struggling with.
Yeah, you might be right. But I still think that, I argued even in my PhD dissertation that meaning, like the meaning of, say, an increasing sequence is the ability to recognize it in many different contexts. And this, if a program can do that, even in these idealized contexts, it doesn't have the richness of a human meaning, but it is abstracting meaning in the world that it's working in. I don't think that it is true for a lot of, like traditional AI systems or deep learning systems, because I don't think they don't think they have the flexibility to recognize things in very kind of more open-ended contexts. But I think it's a great point, and it's something that I also feel conflicted about as well. So,
Thanks.
I guess I want to defend the idealized world, partly because in my master's thesis I also worked on sequence problems, and when I gave a presentation, I think in 1982, it was Doug Hofstadter who came to my defense and said,
"All right, thanks, Tom."
Important thing. So I'm going to return the favor indirectly. I mean, there basically hardly anyone in AI is studying abstraction. We don't even have a good handle on how to approach it. And so I think this is clearly one potentially fruitful path to pursue. And if we don't like this one, we have to come up with something else. And we don't seem to have anything else. So I really like the idea of trying to get our hands on a sort of Drosophila of abstraction that will let us very cleanly formulate the issues and try to make some progress. So
thanks.
I'm eager to see what happens with this line, and also with Cholet's challenge. Yeah, it's great for the community.
Great, thanks.
And we have a question from Connor.
Yeah, I have a bit more practical question, but I was just wondering how you can actually define the ground truth for these analogies. For example, if we take the example of the letter string analogies you present, actually there are many possible solutions, and actually, since you have only one example, all solutions are almost equally equal, including like the output sentence is just randomly generated. And so from a, let's say, a computational point of view, I was just wondering how you actually determine the ground truth for training your system. And then from more like human-centered perspective, I was wondering if you have some ideas of what kind of actual prayer or in which order that should be applied in order to well reflect what most humans would do here as an analogy.
Yeah, no, that's a great question. So this is different from your typical, machine learning paradigm where you have labeled examples and you learn from them. Here, there's no learning. We built the concept network, and we built, there's no training period, and there's no ground truth. So it's different there, and in fact, the system's stochastic. It comes up with different answers on different runs sometimes, and you can kind of look at the distribution of answers it gives. There's no feedback to the system the way that it works. And you can say, you can ask, did I kind of capture the distribution that human answers to these problems, which is what I did in my work. That's not to say that it's necessarily, there are certain analogies that humans are much more likely to make, and some that they find ridiculously dumb that they would never even have thought of. It's funny because the program comes up with really dumb analogies sometimes, and humans laugh at it because it's hilarious. And I think that's good because it kind of shows that we do agree on a certain kind of abstraction as being the correct one. There's no formal proof that it's correct, but it's just the way we are, our brains work, and you can kind of look at how well the program kind of distributes its answers among the human-like ones and among the non-human-like ones. So, it's a hard thing to, as I said, there isn't really a fixed ground truth. People like Cholet and Raven, when he was designing his problems, were more concerned with trying to come up with, like, there's only a single right answer. So there is kind of more of an accuracy measure you can make, but on our letter strings, we didn't have that.
Okay, that's understood. Thanks.
And we have one more question from the Q&A section from Mihandrish. How do you see the relationship between abstraction and lossy compression, which we understand well?
Well, compression, abstraction is a kind of compression probably, but it really depends on the representations that you're compressing, right? And so the key to abstraction is getting the right representations. So I don't think there's like a compression algorithm that you can apply to these things without having some kind of notion of representation. So, in the sort of deep learning world, people talk about sort of, here's this vector space. You want to find the right high dimensional vector to represent things. And then you look at things like, if all these things have this kind of, you can do a clustering on vectors and do some kind of compression that way. But that wasn't how, in these domains, that isn't how I was approaching it at all. So I don't know. I don't have a great answer to that question.